This is the second part of the network models on maximum flow problems. In the previous part, I've introduced some problems that can be modeled as maximum flow problems. Here in this video, I'm going to talk specifically about the method to solve those problems to obtain the optimal solution. So Ford-Fulkerson are the names of the people who invented or developed this method. So first we start by assuming that a feasible flow has been found. The simplest way to do this is we are letting the flow in each arc equal 0. In other words, we just start with flowing nothing from the source to sink. It's feasible, right? Because you are flowing nothing, then you do not violate any capacity of the arc, and then you do not violate the conservation of flow constraints. So this is a feasible solution. You're flowing nothing from the source to the sink. And then we have two questions of interest after we start with that feasible solution. So the first question is, how can we tell if it is an optimal flow? In other words, how can we tell that the solution has already maximized x0? If you don't have any idea what x0 is, you really need to go back to watch my first video on maximum flow problem, okay? And then question 2. Suppose we already know that this feasible flow is not optimal. How can we modify the flow to obtain a new feasible flow that has a larger flow from the source to the sink? So question 1 means that we are asking, how can we know if this is optimal or not? Question 2 means that if we know if our solution is currently not optimal, how can we improve it? How can we add more flows from source to the sink? We're going to answer question 2 first. The method will have the concept of increase and reduce. So I'm going to start by introducing the concept of increase. So I think you're quite familiar with this kind of situation, especially if you're living in big cities in Indonesia before the pandemic. So you must be able to relate to this situation. So there's a road that is quite wide that have the capacity for several cars. But then for some reason in the middle of the road, there's something that causes the road's capacity to shrink. Let's say in this part you can fit 5 cars. Now only 2 cars can fit here. So everybody will start to push themselves into this part of the road. And then after a while, it goes back to the wider capacity of the road. So it can again contains more cars. What I'm going to show you here is that suppose in this situation, we only have 1 car on each section of the road. So 1 car in the widest section, 1 car in the narrowest section, and then 1 car in the in this final section. Let's assume again that all these cars have exactly the same speed, so no cars can get ahead of the others. Okay, if you look at this scenario, it means that in each unit of time, you will have 1 car getting out of this network, right? Because 1 here, and another 1 here. The result is in a single period unit of time, you get 1 car out of the system. Now you can notice that in the first section of the road, actually you can still increase the number of cars that flows through this section, right? Same thing in the second section of this part of the road, although it is still very, it is already very narrow, I mean, you can still have some space to increase the number of cars that can squeeze through this part. Let's say you can increase this into 2. Same thing in the third section, you still have some empty space to squeeze some car through this part of the road. So this is what the increase idea says. It says that you still have the space to increase the flow in that section of a road. So this increase property is specific to each section of the road. So in the maximum flow problem, it is specific to each arc in the network. Why do we need to bother with the idea or property of increase? Well, if you think about it, suppose we increase the number of cars that flow through each section of the road in the previous example from one car to 2 at a unit of time, you can see that the result is in every unit of time, we have more cars that can pass through this network of streets, right? So if you increase the number of flows that are flowing through the streets, then the result is you get more cars flowing out as well. So that is quite logical. You increase the flow if it is still possible, and then the result will be more. Now let's go back to the very beginning. We have one car flowing through this section of the roads at 1 unit of time. And then we can see that we can increase the number of cars that are flowing through. So we increase it into 2 cars at 1 unit of time. Now you may think that we still have some space to increase the number of cars here, right? And also here. Well, if we try to increase it up to 3 cars at a time, we cannot do this because in this part of the road where it is the narrowest, you cannot fit 3 cars at that part, such that you cannot have 3 cars at a time flowing out of these sections of the road, which means that this solution is not feasible. So you can notice that when you have a set of sections of the roads that you can increase, the amount of increase of the overall network is determined by the narrowest section of this road. Remember, you can only increase 1 car here, and the other sections must follow to increase only 1 car, despite they're having some space to increase more than just 1. So that's an important concept to remember. Now, just like every good movies or novels out there, there's a plot twist in this method. So the plot twist here is that in order to improve your solution, which means that you have more amount of things that is flowing from source to sink, sometimes you cannot only rely on increasing the flows. Sometimes reducing the amount of flow in some arcs is also useful. So reducing means that if you have an arc that is already filled, whether partially or fully filled, it means that this arc or this part of the road has the potential to be reduced. Okay, so here in the second part of this road, you can reduce it. In the first part of the road, you can also reduce this. Of course, in the first part of the road, you can either increase this part or reduce it, right? Because you still have space to increase it, but it's also already partially filled, so you can also reduce it. So here in this example, in this particular example in this slide, you may not see how or why reducing the flow through an arc may result in a better overall flow. But then later in the more complete example, you will see that sometimes the combination of increasing this part, reducing that part, results in a better solution than just relying on increase, for example. Okay, so these are the concepts of increase and reduce. Now let's see the algorithm more formally. More formally, the algorithm describes or defines the property of an arc like this. The first property is about the increase property, which is denoted by a big I. And then the second property is about reduce, the big R. Let's see what it says formally. It says the flow through an arc ij, if that flow is still below the capacity of an arc, in this case, the flow through that arc can be increased, and then we'll let this big I represent that possibility. So here, let's see, from source to sink, the actual flow right now is 1, the capacity is 2. So this arc has an increased property. Let's try to check another arc. Suppose you are trying to check whether 1 to sink is also an increased arc. You can see that it's not, because the actual flow right now is 1 and the capacity is exactly 1. So you cannot increase this arc. So 1 to sink is not an increased arc. Now let's see the second property. It says if the flow in arc ij is positive. This is very important. It's positive. It does not say it is full capacity. No, it just say it's positive. Okay. If the flow in an arc is positive, it means that we can reduce it. Okay. Let's check again from source to 1. The current flow is 1. 1 is positive. So any number of flow that is positive means that this arc has also the potential to be reduced. So arc source to 1 has both properties. It has the property of increase. It also has the property of reduce. What about the arc from 1 to sink? The current flow is 1. It is positive. So again, if the flow is positive, definitely it has the reduce property. Let's check another one to make sure you understand this concept. The arc going from 2 to 1. The current actual flow going through this arc is 0. The capacity is 3. It means that we can increase the flow going through this arc, right? The actual flow is 0, the capacity is 3. Now check if we can reduce it. So the current flow that going through this arc is 0. 0 is not positive. Because 0 is not positive, we cannot reduce this arc. Well, logically, if nothing flows through an arc, what would you want to reduce? Right? Of course, nothing you can reduce because nothing flows through that arc. So this arc 2 to 1 only has the property of increase. We start this method from the feasible solution of the network, in which we just leave the flow through every arc equals 0. So do nothing with the network and it's already a feasible solution. Okay, so do not put any flow on any arc. Just leave everything 0. Now in the step 1, we start with labeling the source. By label here, it means that above the node of the source, you put a small star or an asterisk. And then in step 2, we are going to use the property of increase and reduce that we just discussed. And then let's see how we can use that properties of increase and reduce. So step 2 says we're going to label nodes and arcs except for the artificial arc according to the following rules. Okay, let's see. If node X is labeled, node Y is unlabeled, and the arc XY has a property of increase, then we can label node Y. So this is the illustration. So node X has been labeled. So somehow we have labeled this, means that we have put a small star or asterisk. And then it says if node Y is still unlabeled, you see there's no star here. If node Y is unlabeled and these arc XY has the possibility to be increased, it means that we can label this Y and call this forward arc. Okay, so you are in the situation, let me repeat, you are in the situation where you see a node X that has been labeled by a star, and then you see node Y without any label. You see the arc is increased, then you can label Y and say it is a forward arc. There is another possibility. So this is the plot twist that I was talking about. If node Y is unlabeled, node X is labeled, and the arc YX. So notice here the arc is YX, not XY. So the arc YX is a member of reduce, then we can label node Y. This is the situation. We see node X has been labeled. We see an arc YX has the possibility to be reduced. Then we can label Y. And then we call this backward arc. Backward because we have X already labeled. The arc going from Y to X but has a potential to be reduced. Then we label Y. Call this backward arc. Then we continue doing this labeling process, putting this small asterisk in above of the nodes until the sink has been labeled or until no more vertices can be labeled. So it says until we can label the sink, or we cannot reach the sink, but we do not have any way to go forward. Now let's apply those 3 labeling steps to this example. So first we need to start with a feasible solution, which means that you just make everything, every flow in every arc equals 0. So do nothing. So the ones in the parentheses are the capacity, and the one without parentheses is the current solution. So everything is 0. Nothing flows through this arc. Now let's start with the labeling procedure. In step 1, we always label the source. So we did put an asterisk there. And then suppose I'm considering this arc from source to 1. Can we label 1? Well, according to step 2, if this has been labeled, and then if the arc has the potential to be increased, in this case, yes, because the current flow is 0, but the capacity is 2, then yes, we can label node 1. Now from node 1, I can go to either 2 or 3, and suppose I'm taking the arc 1 to 2. Now think about if node 1 is X and node 2 is Y. Just like before in the step 2, it says that if node X has been labeled and the arc XY has a potential to be increased, which in this case, yes, because the current flow is 0, but the capacity is 3, then we can label node Y or node 2 in this case. Now let's take a look at node 2 to sink. Again, we have labeled node 2. The arc from 2 to sink has the potential to be increased. So yes, we can label the sink. Now this is complete from the first step, labeling the source, until step 3, labeling the sink. So we have finished the labeling procedure. Of course, if you take another route, let's say you go from node 1 to 3, the result will be different. But do not worry about that as long as you follow the procedure, first starting with the source, and then last trying to label the sink, if possible. After we did the labeling procedure from step 1 to step 3, we will obtain a chain of labeled arcs. We call it big C. So let's get back to the previous example. After we finish labeling the nodes and we reach the sink, we have this chain of labeled arcs. Source to 1, 1 to 2, 2 to sink. So that is our C. Now it says that by adjusting the flows in the arcs in C, we can maintain feasible flow while increasing the total flow. So we can keep the flows satisfying the capacity constraint, but we can also at the same time increase the total flow, which has something to do with this C. How can we do that? Well, we need to look at what kind of C that we have. In case 1, the C consists entirely of forward arcs. This is exactly like what we did in the previous slide. From source to 1, it is a forward arc. 1 to 2, it is a forward arc. 2 to sink is also a forward arc. So this example belongs to case 1. However, there is another case actually, which is called case 2 here. Case 2 is the case where the C, the chain that we have after the labeling process, contains both forward and backward arcs. In any of those cases, either case 1 or case 2, we can do something to obtain a new feasible flow with a larger flow. Okay, so next we are going to see what we're going to do if we have the big C, which belongs to case 1, and the big C that belongs to case 2. Let's look at case 1 first. So this is the case where our chain consists entirely of forward arcs, just like the example that we did in the previous 2 slides. They're all forward arcs. What can we do? So here we are recording IXY, which is the amount by which the flow in arc XY can be increased. So for each arc here, source to 1, 1 to 2, 2 to sink, we record how much we can increase at this part. So this is become I from source to 1 equals, let me see, equals 2. Why? Because currently there's zero flow going on from source to 1 and the maximum capacity is 2. So the number of the amount of flow that we can increase along this arc equals 2. We do the same thing for each arc in our chain. So do the same thing from 1 to 2 and 2 to sink. And then we take the minimum of them all. So minimum of all arcs in the chain. And we denote that value as K. So if you recall the example at the beginning about the cars in the street, This is why I said if you have several sections of the road where some sections is narrower than the other, then if you want to increase the flow through all sections in that road, then you need to consider the minimum. Remember when I said that why we cannot increase from 1 car to 2 cars is okay, but then from 2 to 3 is not okay. So this is formally why that is the case. So you have a chain. If everything is forward arcs, you record how much you can increase in each arc. And then you compare for every single arc, take the minimum that you can increase the entire chain. So that is the value K. And then to create the new flow, you increase each arc in C by K units. Now the new flow is feasible and it will transport K more units to the sink. Now let's apply what we have just seen about case 1 in another example. So suppose we have the current solution that looks like the figure on the top of this slide. So this one. Which means that from source to 1 we have the flow of 2 out of the capacity of 5 of this arc. From 1 to 2, of course, the flow is 2, and from 2 to sink, the flow is also 2. So we have the flow from source to sink equals 2. So we are not talking about how we can get that value 2. We just suppose that we have this solution, okay? Now, once we have this, we're doing the labeling procedure. So first we label the source with an asterisk. And then we see that from source to 1, it is a forward arc. It is a forward arc because we still have the potential to increase this. The current flow is 2, capacity is 5. So yes, this is an increased arc. So yes, we can label 1. With the same reasoning, we can label 2. And then with the same reasoning, we can label sink. And all we have here is just forward, forward, and forward arc. So this is the chain. From source to 1 is a forward arc. 1 to 2 is also forward arc. From 2 to sink is also forward arc. Since all arcs in the chain are forward arcs, so this is case 1. So for case 1, we need to find the K, which means that we need to find out how much we can improve on each arc. So from source to 1, current flow is 2, capacity is 5. So we can increase it by 3. From 1 to 2, current flow is 2, capacity is 3. So we can increase by 1. From 2 to sink, the current flow is 2. The capacity is actually 4. So we can increase this by 2. Now remember, K takes the minimum among all these values. So K is the minimum of 3, 1, and 2 in this case. So 1 is the minimum. So K equals 1. Next, what are we going to do with this K equals 1? Well, what you're going to do is that you increase every single arc in that chain with 1. So you notice that previously it was 2, now becomes 3. This is also 2, becomes 3. Here it was 2, now it becomes 3. So now the flow from source to sink is improved from 2 to 3. So that's how we can use case 1 to improve the total or the overall flow from source to sink. Now let's move on to case 2. In this case, our chain contains both backward and forward arcs. We haven't seen this kind of example yet, but we will. So for every single arc in the forward arc, we try to record how much we can increase for each arc and denote it as IXY. This is just similar to case 1. For all the arcs in the backward arcs, we record RXY, which means that how much we can reduce the value on those arcs. And then we separate them. So for all arcs that can be reduced in the backward arc, we take the minimum and denote it as K1. For all the forward arcs that we have recorded how much we can increase for each arc, we also take the minimum among them. So minimum here is very important. So whether it is the group of increase or forward arc, or whether it is the group of the backward arcs, which can be reduced, it is the same that we always take the minimum. Okay, so do not forget that we always take the minimum both for the backward arcs and for the forward arcs. So K1 means that among all arcs that we can reduce, we take the minimum value. K2 means among all arcs that we can increase, we take the minimum value of increase. So K1 is the minimum value of reduce that we can do. K2 is the minimum value of increase that we can do. And then the interesting thing is that after we find K1 and K2, we take the minimum again. So K1 is already the minimum among all reduced or backward arcs, and K2 is already the minimum among all increase or forward arcs. We take the minimum again among K1 and K2. And then we use that minimum to decrease the flow of all backward arcs. We use the same minimum among K1 and K2 to increase the flow of the forward arcs. So if we have mixed types of arcs, we have backward and we have forward, then we will decrease the amount for the backward arcs, and then we will increase the flow for the forward arcs according to this value. To compare this with case 1 because all arcs are forward arcs, so we simply increase everything with K. Here, because we have a mix of backward and forward, so we decrease the backward using the minimum of K1, K2. We increase the forward arcs using the minimum of K1, K2. By doing this, again, we will keep the conservation of flow constraints, make sure that no violations is made for the capacity of each arc, while at the same time we will increase the total number of flow that flows from the source to the sink. Now let's see the case where case 2 may happen. So again, suppose somehow we obtain this kind of solution. Okay, so we're not talking how or why we can get this kind of solution, but suppose we are at this solution somehow. Now, as usual, we start by labeling the source. Now, if you try to label 1 using source to 1, it is not possible. Why? Because from source to 1, it is not an increase arc. It is not a forward arc. Source to 1 is a reduced arc. Current flow is 2, capacity is 2, so we cannot increase anything. That's why this is source to 1 is not a forward arc, so we cannot label 1. So what we can do is that we're looking at this arc, source to 2. This is an increase arc, so source to 2 is a forward arc, so now we can label 2. Next, you're trying to go from 2 to sink. But again, 2 to sink is a reduced arc. So you cannot label sink, because if you want to label sink, 2 to sink must be a forward arc. However, now you check the other possibilities. 2 has been labeled. 1 has not. But this arc has the potential to be reduced. So now, using the procedure of backward arc, you can label 1. Okay, so let me repeat. 2 has been labeled. From 1 to 2, this arc has the potential to be reduced. So this is a backward arc, and you can label the node 1. 1 to 3 is simple. It is a forward arc, so you can label 3. And then 3 to sink is also a forward arc, so you can label the 3 to sink. So up to now, all the yellows, they are forward arc, and the other color is backward arc. So really have to notice how I did the backward labeling using the backward arc. Now what we can do is we're trying to find K1 and K2. So K1, so for K1, you have source to 2, which can be increased by 3. You have 1 to 3, which can be increased by 4. You have 3 to sink, which can be increased by 1. Take the minimum of this, so K1 equals 1. Now for the K2, how much can you reduce the flow from 1 to 2? Well, the current flow is 2, so you can reduce at most 2. So because there's no other backward arcs, so K2 equals 2. Now the minimum of 1 and 2, the minimum of K1 and K2 equals 1. Because K1 is 1, K2 is 2, the minimum of 1 and 2 is 1. Now you increase every forward arc with 1. So that, and that has been increased by 1 from the previous solution. So see here, it was 0, now it becomes 1. So all the yellows here has been increased from the previous solution by 1. And then for the backward arc, you see now the value here is 1. Because we reduce the flow from this arc 1 to 2, we reduce the flow from 2 previously to become 1. Now surprisingly, even though we have a reduced arc, we reduce something in the flow, the total flow from source to sink is increased. Previously the total flow is 2, now the total flow is 3. It's very interesting and it's not difficult. You just need to really realize that, oh, using this kind of thing, you can have you can label the backward arc and have case 2. Okay, so back to this part. So you cannot just give up when you label source to 2 and then you cannot label 2 to sink and then you just give up. No, you must try to find any way that can make you label the sink if possible. So this is the end of the part 2 for the maximum flow problem. In the part 3, I'm going to talk about some examples that we really see how we can apply the labeling procedure, look at the cases, and improve the flow until we get the optimal solution. Also in part 3, I'm going to talk about how can we tell if our solution is indeed optimal. So see you in part 3.